Bismillahirrahmanirrahim. Assalamu alaikum. Today our topic name is Fourier series. So we define it as the series that are used to approximate the function f by polynomials are number one, that is the Taylor series, and the number two is the Fourier series. Number one, Taylor series. In this series, polynomials give a close fit to the function f near the point x is equal to a. So what do he say? It says that in this series, polynomials gives a close fit to the function near the point x is equal to a. Why this series becomes failure? It fails at that point where the error of the approximation can be very large. Where this error of the approximation can be very large at those points which lie far away from x is equal to a. This is the way. That's why this series gets failure. Number two, the Fourier series. This series gives good approximation results on wide intervals. So therefore, it is often work with discontinuities. It means some way they generate some jumps when there is some jumps. That's why function become discontinuous. So therefore, it is often work with discontinuous functions for which the Taylor series fails. The inventor of this work is Joseph Fourier, who approximated the function with sum of sine and cosine function. The advantages of this series are: it is well suited for the analyzing the periodicity of the functions, such as reduced signals and alternating functions. And such type of functions you can represent them by the diagram which you have studied in your physics. What type of graphs of the reduced signals and alternating current produce. In the same way, the second part is the ingenious idea of Fourier's analysis is to represent the complicated function in terms of simple periodic functions, namely cosines and sines. So why we say it is used to represent, or it is used to analyze the complicated functions. These functions are of the following form. Such type of functions are so called complicated, or what I say in point number one, the complicated or discontinuous function. These are the discontinuous functions. As you see here, from 0 to pi, the value of the function is 1. When we move from pi to 2 pi, the value of the function is 2. So you see here there is a jump. Or you say it is called the discontinuity. In the same way here, when you move from 0 to minus pi, the value of the function is minus k. And when you move from 0 to pi, the value of the function is k. So there is also a discontinuity in this way. There is a jump between. So in the same way you see further at different points. Here is another example that we use. This is expressed in the mathematical form in a form of piecewise function f of x is equal to minus k to k. If the value of the function is minus k when the value in that interval which contains 0 to minus pi. So the value of the function in the interval 0 to minus pi, the value of the function is minus k. And the value of the function is k when the interval is 0 to pi. Here is another example. As you see here, these are represented by some lines, 0 to minus pi or 0 to pi. So such type of functions you see in the half wave rectifier in your electronics and some other functions. So now the representation will be infinite series called Fourier series. Such type of pattern you can't say that this pattern is for a closed interval. It might be some infinite. This interval repeat itself in infinite on a real line number. So, and you know that the number of real lines are infinite many. So there is a series generate such type of function is called the infinite series, and that infinite series is called the Fourier series. Now we move toward how we generate such type of Fourier series. And you see here, suppose we want to find the sum of the sine and the cosine functions in terms of in the form of a single function on the interval 0 to 2 pi. Let's say we suppose our interval is 0 to 2 pi. Here fn of x is equal to a0 cos 0x plus a1 cos 1 of x plus a2 cos 2x plus so on an cos nx plus b0 sin 0x, b1 sin 1x, b2 sin 2x plus so on bn sin nx. And you know that cos 0 is equal to 1 and sin 0 is equal to 0. So here this term remains, but at this point this term vanishes. So our other terms are, as you see here, fn of x is equal to a0 because a cos of 0x becomes 1 and remaining is a0 plus a1 cos of x, a2 cos of 2x plus so on an cos n of x. These are the terms remain in the cosine function, and other are the sine, the terms of the sine functions in summation form. And we also express such type of function in a in summation form, and you see here the subscript of a is here 1 and the angle is, the coefficient of the angle is 1. Here the subscript of a is 2 and angle is 2. In this way you see here, if we want to write such a big expression in a smaller way, you use a summation expression. In summation form, the above expression is written as fn of x is equal to a0 plus n is equal to 1 to n is equal to infinity. So an cos nx plus bn sin nx. Here a0, an and bn, these are called the Fourier coefficients. These are called the Fourier coefficients, and later on we will calculate their values, how we can compute their values. And now, and in most general form it can be written as over the interval minus p to p or minus p become anything, any real number. It is 0, pi, 2 pi or some other way. So its general expression is f of x is equal to a0. You see here a0 plus summation n is equal to 1 to n is equal to infinity an cos n pi x over p plus b sin n pi x over p. Just we see this, we are not going to how to generate such type of expression, how this angle, just we work on the Fourier series. This expression is called the Fourier series. This expression, this f of x is called in the form of equation number 1, it is called the Fourier series. And I'm also telling you the a0, an and bn are called the Fourier coefficients. I am writing here where a0, an and bn are called the Fourier coefficients. Now the values of these Fourier coefficients are, I am writing here by the name of constants. The values of these constants or the Fourier series are a0 is equal to 1 over 2 pi from minus p to p f of x dx, an 1 over p minus p to p f of x cos n pi x over p into dx, and the last one is bn is equal to 1 over pi minus p to p f of x sin n pi x over p into dx. As you see here, its interval is minus p to p. Such type of intervals are called the periodic intervals. The periodic interval, because if the interval is periodic, it means function repeat its properties over and over. The function repeats its properties over and over. As you see in the half-wave rectifier in the DC circuit and the AC circuit, when you see in the AC circuit, you have a sinusoidal wave in a form of sine wave, and in a DC circuit you see there it's negative, the negative portion of the sine wave vanishes, the only remains the positive way of the series. In the following manners we calculate the values of the Fourier coefficients. In the following manners we calculate the values of the Fourier coefficients. Before this I am defining some basic properties that are used in obtaining the results of the Fourier coefficients. Number one, in the periodic interval cos m pi x over p cos n pi x over p dx is equal to 0. The value of this function becomes 0 if m and n are not equal, where m and n are the any real numbers. Let's say if m is some number and n is some number, let's say m is equal to 1 and n is equal to 0. So this total function becomes 0, and the only terms this become if the value of n is 0, then you see here cos 0 is equal to 1. Cos 0 is equal to 1, and cos the remaining functions are the remaining function is cos m pi x over p. And when you open this function or you integrate this function over this periodic interval, its value becomes 0. In the same way with the sine function, if m and n are not equal, if you integrate their product in a periodic function, its value also equal to 0. Or some way you say that you have to make a product formula. If let's say if n is not equal to 0 or m is not equal to 0, if there are some numbers, then it becomes a product. You have to multiply and divide it by 2, and then you integrate over this periodic interval. Here you see also these are some results of the product formula. Then you convert these function by multiplying and dividing by 2 and integrate over this periodic interval, their values become 0. And these are the prior conditions. You have to see that if the values of m and n are not equal, or in this case if m and n are equal, these are the result in which functions get value 0 when you integrate over the periodic interval. These functions are called the orthogonal functions. Why we say these functions are called the orthogonal functions? If the product of two functions is equal to 0, then we say these are called the orthogonals. In the same manner you studied in your intermediate mathematics, when two functions are perpendicular to each other, then their dot product is equal to 0. Here we say these are called the orthogonal functions. If these two functions are orthogonal, then their product is equal to 0. Now we want to calculate the values of the Fourier series, Fourier coefficients. Let's see here. If we integrate the equation number 1 on both sides from minus p to p, we get. Here you see I take the equation number 1, that is I am integrating it from minus p to p on both sides, as you see here. If you integrate here the expression which is enclosed in the square brackets, here the integral of cos, when you open the integral of cos in a periodic interval, its value becomes 0, and when you integrate this function over the periodic interval, its value also become equal to 0. You can calculate it by integrating it. You see this. If you feel any problem, then you solve this and send to me by WhatsApp. I am explaining you. So this total expression becomes 0. The only the expression that remains is a naught minus p to p dx. The value of I am writing here the value of minus p to p cos n pi x over p dx and sin n pi x over p dx in a periodic interval become 0. So the remaining terms are minus p to p f of x dx is equal to a naught minus p to p dx. Minus p to p f of x dx is equal to a naught. When you integrate this, you get x from minus p to p and substitute the limits, you get a naught p plus p is equal to 2p a naught. So we simplify this for a naught. A naught is equal to, by dividing 1 over 2p on the other side, you get 1 over 2p is equal to minus p to p f of x dx. Here in this way you get the value of the first Fourier coefficient. Now we move toward the other, how we can find the value of the an. By we obtained its value by multiplying equation number a by cos n pi x over p on both sides. First you multiply equation a by cos n pi x over p on both sides, and then you integrate it from minus p to p. And you see here minus p to p f of x cos n pi x over p dx is equal to a naught minus p to p cos n pi x over p dx. And here you see when I multiply with first term, I am showing you when you multiply with cos n pi x over p. First you multiply cos n pi x over p here, then you multiply here, then you multiply here. When you multiply cos n pi x over p here, it becomes the square, and it becomes sin n pi x over p, then cos n pi x over p. Here I am writing here as you see. Now I am defining before this the value of cos n pi x over p over this periodic interval becomes 0, and here by using the basic properties idea, the third one, the product in this interval is equal to 0. So the remaining terms are this is our remaining term. So the terms is in the red and blue. This is red and this is blue, goes to 0. So the remaining is minus p to p f of x cos n pi x over p dx summation n is equal to 1 to n is equal to infinity a n minus p to p cos n pi x over p whole square. You know that when trigonometric functions are in a square form, their integral does not exist. You have to convert them in double angle formulas. I am using double angle property of cosine function. I am writing here it as a n minus p to p 1 plus cos 2 n pi x over p divided by 2 into dx. So after simplification you get f of x cos n pi x over p dx is equal to a n 2p over p is equal to a n is equal to p. When you integrate this, you take this 2 outside from the integral, it becomes a n over 2, and when you integrate with respect to x this 1, it becomes x, and the integral of cos is sine. And when you evaluate this sign after simplification at minus p and p, the value becomes 0. Its value becomes 0, and therefore I am after simplification I just write after simplification you get. This is simple integration you do here, the simple integration here, and we get a n is equal to 2p over p is equal to a n p. Hence minus p to p f of x cos n pi x over p into dx is equal to a n 2p over p is equal to a n p, and by dividing p on the other side you get a n is equal to 1 over p minus p to p f of x cos n pi x over p dx. Similarly, we find the value of bn by multiplying equation a by sine n pi x over p on both sides, as you in the same fashion as you done in finding the value of a n. At that time you multiply both sides by cos n pi x over p. Now we multiply here on both sides sine n pi x over p to find the value of this bn, this coefficient bn. So in the same way you get bn is equal to 1 over p minus p to p f of x sine n pi x over p dx. This is a small type of what I say, it is a assignment for you. You have to find the value of bn and then send to me. Inshallah ta'ala we will meet in the other next lecture with some applications on and with some problems, how to solve the questions by using these coefficients in our problems and find their Fourier series. Till then, okay, Allah Hafiz.